All right, good morning. How you guys doing? Finally have a bit of winter here. Huh? Always interesting the difference in the cold. So I spent 2 years in Michigan, and when it got into the 40s range after winter, everybody was like really excited to be wearing shorts and things like that. But part of the difference is how much humidity there often is in the south when we get a cold front. And that humidity, all that water saps the heat from you a lot quicker than dry air would. And so I think that's a big difference. And if you ever have some friend that comes south from the north and then they're like experiencing the soggy, wet 40-degree weather in winter, I think a lot of them are surprised by how cold that is. Like, oh no, I've lost all my wintry my thick blood or whatever. Probably just thermodynamics, but okay. So we left off last time here. We had this is basically the last slide of our set. We had derived a mass balance on X to solve for S for this particular pond problem where we have BOD being removed by microbe action, so microbes eating the substrate food. Both the substrate and the micropopulation will change in this system, so that was a complication. In this particular case, we could simplify it by first solving for the substrate, the mass balance on X. That was true in this particular case because X naught was 0. That meant right here in this equation, we get a 0 right there, which ultimately led us to have an X on both sides of the equation. Just happens to simplify very nicely. Okay, so that's not promising that's going to be the way of it always, but I'm giving you this equation here that we derived to say that if we do have a pond situation where we assume there's no inflowing bacterial concentration, there's just some bacteria growing in it, and it's acting like a CSTR, again, no recycle sort of situation going on, we can model it that way. So then we went on, answered these problems, and we left off here to solve a mass balance on S. So I figured I'd finish that off before we start kind of the second set of slides for secondary wastewater treatment. Okay, so when we want to solve for X, counterintuitively, we're going to then solve the mass balance on the substrate here. So mass balance on S, we started to set it up. We said 0 equals Q S naught, so the amount coming in, minus the amount leaving, QS, plus the effective rate of substrate utilization in that entire pond's volume. So that's the VRSU. And that's substrate utilization, so this will become a negative once we expand out that RSU. So as we see, we'll insert here the negative x, lowercase k times s divided by ks plus s. That all came from taking that growth equation and adapting it given the yield coefficient that we know. Okay, so that's all this stuff here. So once we do that, we can then start working to simplify this. We'll go ahead and insert it. So QS naught minus QS minus V times this stuff. So it'll be X. This is that lowercase k that does not have a subscript, divided by KS plus S. So that's going to be our system here. We can go ahead and divide everything by Q. We'll have 0 equals S naught minus S minus theta times X KS over KS plus S. Okay, from here, let's see. Let me find my spot in my notes real quick. on the wrong page, that would be why. Okay, from here, what I'm going to do is separate out S as best I can. So what I'll do, let's see. Excuse me, separate out X, of course. Solving for X, right? So I'm going to get the X term on the left and just simply work on simplifying to solve for X there. Because we know S because we solved that in part A. So we'll say theta times, I'll just go ahead and bring the X out front, times KS plus S equals S naught minus S. So basically now we just need to divide by theta and divide by this stuff, and we'll get an equation for X, which would equal S naught minus S. We're going to have to multiply this by this KS plus S. And then all of that will be divided by the theta and the lowercase k and the S. Okay, so that gives us a term for X in terms of all the variables that we now know, because we were able to solve for S. And once we put all that in, we can get an X value of 43 milligrams VSS per liter. Okay. All right. What's up? So again, I'm going to give you this equation, this X equals this stuff. Again, this is very specifically to the scenario where we have the pond situation. So just wanted to let you know that's when it's relevant, and that's where that can be used. All right, so I'm going to save that and bring up our next one. Okay, so today we're actually going to talk about the slightly simpler case where we have recycle. The reason that's slightly simpler is because we actually regulate the X in the system. So X ends up staying constant because we're recycling, or it can stay constant. So this recycle, really what we're doing is recycling the bacteria. This is going to mean that we have kind of an interesting mass balance. At the end of the day, it's going to be simple. We'll spend the first couple slides here talking about how we are mapping out this mass balance and the assumptions that we need to make. But at the end of the day, it does become a little simpler than it would look at first. Because at first glance, we have, okay, this recycle line that's adding flows in weird places, and what do we do with that in terms of the flow? And then we have not only this aeration tank, but we're also drawing this boundary around the secondary clarifier. So like what all is going on here, and how do we make sense of that in terms of a mass balance? Well, as you'll see here in this graphic, our book drew a control boundary around the outside of that recycle line. So at the end of the day, the water that's going in and out is going into that control boundary here and out into spots. And so we don't actually have to worry in terms of like the hydraulic side of it. Hydraulic retention time is not going to be affected by the recycle, because that's all captured within that system. There's going to be a couple other assumptions. So I'll talk about them with them all listed on the next slide. But if we think about the clarifier here, it's separating all this bacterial matter. Essentially what's going to happen is our effective X in the effluent should go to 0. Or at least that's the assumption we'll make. So that's going to simplify the solids management. So when we think about the mass balance on X in this system, we really only have one entrance and one output. Not only that, but we're going to operate it in such a way where we try to keep X in the tank constant. So we'll be able to reach a steady state in a system like this where we're continuously removing S, continuously increasing X, but keeping them at a steady state within the system, right? So given that, there's a few assumptions we have to make. First of all, that, like I just mentioned, that clarifier is perfect. So XE goes to 0. This is a particular assumption that it means we really have to take good care to keep the right bacteria in our system. I think maybe I mentioned this last time, but there are some filamentous producing bacteria that like to eat particular stuff. So if we accidentally give them a diet that is much more rich in lipids, let's say a new restaurant opens and starts dumping a whole bunch of grease or something, there's a chance that something like that, or a change in pH, even a change in temperature, could trigger a different microbial population, give them the right conditions to outcompete the other bacteria that we're normally used to growing that flocculate nicely and are removed from the clarifier. So if we get this filamentous production, all of our bacterial mass starts floating because of the filamentous nature and then the bubbles that we're adding. Then all our sludge floats and escapes, and we have lots of problems because, well, A, we have a whole bunch of bacteria being discharged out our effluent that we're not wanting, right? Way too much to disinfect with a simple disinfection step. We need to physically remove them. And B, that means that when we try to recycle our bacteria, we don't have very much there. So then we have much less bacteria in our aeration tank in the first place, and so we're not consuming the food. And it's a bit of a vicious cycle there. So it's really important that the clarifier works well to keep the bacteria happy, to avoid that sludge flotation and all of the consequential problems there. Okay, assuming then that it is working properly, that we have our control over the system, the next assumption that we make is we don't have any meaningful biological activity in the clarifier itself. The reason we're going to make that assumption is mostly for convenience. There's going to be some. They're going to still be munching on the food and consuming some oxygen here, but we're not providing them with oxygen. And at the end of the day, they're not staying there for a super long time. Water is flowing in and we're collecting the water constantly. So we're not treating it as if there's any bacterial activity. That way we can use the volume of the aeration tank for our reaction. So when we say R of G or R of substrate utilization, the volume here is the volume of the aeration tank. This also applies to theta, would then be V over Q using that V, right? So when we talk about how long the water is spending in our reactor, well, if we have no reaction, no biological activity in the clarifier, then the clarifier volume doesn't matter, okay? So that's sort of the assumption here. What we're dealing with is how quickly is water flowing through the place where the reaction happens, okay? Like I said, it's not a perfect assumption, but one thing it does do for us is, if anything, provides us a slight safety factor, right? It's going to have a tiny bit more treatment in the clarifier, if anything, right? So we're not too worried about messing up the mathematics here by making that assumption. Okay, the next thing we can note, and this is I guess you could call it an assumption, but it also is in a way self-evident, is when we track the substrate concentration, we have substrate coming in S naught, we have some substrate value in the tank itself, we have a substrate in the recycle line, a substrate in the waste line, I guess we could call it, and a substrate concentration in the, again, the waste line here, and a substrate in the effluent. We also are going to have some substrate here, and I'll say S naught prime, I guess, after it mixes with the recycle there. So when we're considering the substrate, this is dissolved stuff. So this is stuff that's not going to be affected by a physical removal of bacteria. So we're not going to be able to sediment our substrate out. That's what we're talking about. It's as if we dissolve sugar in our system, right? The bacteria that eat the sugar are going to form solid objects that maybe we can settle, but the sugar itself is going to go straight through. So that means this, while the clarifier changes the solids concentrations, because it's suspended, it's not going to do anything for the dissolved stuff. So that means the S here that I wrote as effluent, I can just erase that and call it S, because that's the same S that's coming through here. The S that I wrote here and I called it waste, I can erase that denotation because it's just the same substrate. And when it crosses this T joint, nothing happens to the concentration. It's just flowing in two different directions, right? There's no mechanism there that can change the concentration in that liquid. So I can also remove this R for recycle here because it's just substrate. It's just that same concentration. Whatever's in here, it's all mixed, perfectly mixed. It's heading out, just like a CSTR that we are used to, and it's going through the system like that. The only interesting thing is that when we have substrate concentration coming in here, S naught, it will mix with this line, and we have, so, I mean, it's written right here, but to put it in our face here, we could say Q, R, S, R, and this here is Q, S naught, and so this would have S naught prime, I suppose, and Q of R plus Q, or it's like the Q R plus Q, I guess we'll say Q R plus Q. Right here. Okay. So small little caveat there. It's going to dilute the influent concentration just a tiny bit, right? Because we're taking a very small volume of treated wastewater to return into there in order to feed back bacteria. So that should normally be negligible. We'll see in some problems, yes, that we can include it in the calculations. It's not going to make a huge difference. One thing that will matter is that we are diluting our XR here. So we're intentionally getting a high concentration of recycled bacteria, and then it's entering this entire flow. And so ultimately the total input into the tank itself is going to be not a huge number, like it's a huge number in the QR, right? But ultimately we're adding a fair bit of mass one way or the other. So we could also add here this X, I guess, not prime or something. That'll be X naught plus XR, right? Or the mixture of the two, something like that. So we can revisit that later. Okay. Last thing to note here, already mentioned this, is our recycle is going to be the same as the waste. So this X, again, is going to be the same as this X because there's no difference in that split. It's just the pipe goes two directions. And since we have 0x in the effluent, we're always going to have a greater concentration of waste X, so X in the R or XW, than we have in the aeration tank. That's because we are sending a lot of water away with no X, right? assuming we do have flow out here at the secondary effluent, we have concentrated our X. So as if we passed it through a membrane and said nothing escaped the membrane, we've made a concentrate. Okay, so it's very much like that process where we are collecting all the bacteria here, all that X, and sending it this way instead of out the effluent. Okay, so some of that is pretty self-evident, but we'll see how it comes into play for some equations here. And we're going to start with essentially bacteria food as a basis of analysis. So one of the most important parameters for wastewater treatment is called food to mass ratio. And I'm going to term this, as our book does, F/M. So food to mass. This is not a division or a fraction. This is just food. I mean, technically, yes, it's a fraction, food to mass, right? That's the ratio that's being given. But we are not going to use it mathematically as a ratio. We're just going to leave it F/M. A little confusing, apologize for that. But this is what the book is going to say. Do not try to multiply by mass or divide both sides by food or anything like that. Just leave this as is, as one parameter. Okay, so we're going to take that ratio, and that ratio is essentially going to be really important for our biological activity because we have bacteria that are happy, as we learned last time, to grow with a particular amount of food, right? We were even talking about how you could reach their maximum specific growth rate, so maximum microbe happiness, right? That ratio between how much bacteria we have and how much so that's the mass, right? The food being substrate. And then that mass is the X, so microbe concentration. If that's how we are defining it, we'll see that this is going to be some metric for food on top, so milligrams BOD, and some metric for mass on the bottom, but it's actually the way we define it is on a daily basis. It's like the daily food to mass, okay, which puts a time term in that. So I'll just add daily here. So it's not actually exactly food to mass, which is one of the other reasons why we're not going to use it as F divided by M. We're just going to leave it the F to M ratio. So a formula for that then would be Q, so the flow rate times the input substrate concentration, which makes sense. That's how much food that's arriving in the water over time, divided by the volume of the reactor times the amount of bacterial concentration in that volume. So the volume times the concentration is going to yield us a mass, and that's going to be ultimately that's going to happen on top as well. So we're going to get a mass of food divided by a mass of bacteria per time. Okay, so typical units here would be milligrams BOD per milligrams VSS per day. So that's going to give us some estimation of how much, what rate the bacteria are going to grow. That will be somewhat specific to the type of bacteria that are growing. Usually in wastewater treatment plants, we have obviously millions of different species of bacteria present, but usually several of those species are comprise more than 90-95% of the bacterial mass. So it's usually certain specific bacteria, or at least individual species within a class, a couple classes of bacteria that are doing most of this stuff. So if we accidentally let the food to mass ratio get really far away from typical, then we risk propagating some other bacteria, and that might not eat the waste as well. Maybe that does the filamentous stuff and cause flotation, there can be some problems, right? So that's one of the design parameters in some sense, is to try to keep that relatively constant, to keep our culture of bacteria happy. Okay. And I kind of already covered all this. Yeah. So for all these reasons, and again, just to highlight, the mu meaning that specific growth rate coefficient, we just recall that our equation for mu was mu max times S divided by the Ks plus S. So if you change the bacterial species, you recognize that this value would change, and therefore the mu would change. Or likewise, if you're trying to figure out 4 different species that have different ones of these, their specific growth rate, you can see that different ones will operate better given different substrate concentrations. If that makes sense. All right. So that's one term, and this F/m equals Q S naught divided by V times X gives us a handy way to recognize what X concentration we need given some ratio that we have to maintain. Gives us a way to deal with some of these parameters on a very crude metric in some way, right? We were talking last time about the rate at which they're growing and dying, and how does that look like, and okay, what if we have this pond and there's nothing coming in, but there's substrate coming in and there's no bacteria? All of that in a system that's well controlled, and we can maintain this food to mass ratio. Well, we can potentially manipulate one of these things, or see how we could, if we can manipulate X by simply sending more bacteria to waste, then we have control over the food to mass, right? Maybe we don't have control over S naught, that's just what comes through the sewers. We can't really change the volume, but we can change our recycle. That means we have control over food to mass. Okay, so that brings us towards that concept of solids retention time. We'll get there in a moment. First of all, hydraulic retention time. This is, as we discussed, hydraulic retention time, the HRT, the theta, is V over Q, and this is not going to change by the recycle, because the Q here, the net Q running through the system is the same, right? This Q that's coming in, if we add up, so Q would equal QE plus QW. So within this control boundary, we have Q coming in and a net Q going out. That means that recycle, whatever, if we increase the recycle or decrease the recycle, it's not changing the net Q that flows through our reactor. You don't have to apologize for sneezing. So, given, I'm stressing this here because it feels like when we change the flow in the actual reactor by recycling, it feels like it should change something, right? But it's not going to, on the whole, the same amount of water spends the same amount of time there, or the water spends the same amount of time effectively in the reactor. And again, it's only the aeration tank that has the volume, because we assumed that for reaction purposes, the V of the clarifier equals 0, right? But only because we assumed no biological activity. So we're just going to say the clarifier V clarifier is 0. For reactions. It's not actually 0 volume, obviously. Okay, so in the system, no matter what we do with the waste activated sludge versus recycle here. Doesn't really matter. The Q is going to be, the net Q is going to be the same. Our hydraulic retention time is the same. We use the Q that's flowing into the plant, not any calculated Q here that's going in and out here. So we can just use the primary Q, keeps it simple, and our theta is V over Q like normal. Okay, that brings us to the solids retention time. And we see a recycle line flowing in here. Looks quite delicious. So when we talk about solids retention time, we're introducing a new term here, theta C, and here we're going to use that C to denote cell, like microbe cells. Okay, the cell retention time, or solids retention time. Sometimes you'll see it as SRT as opposed to HRT, right? And this one is going to change with the clarifier action, right? Because we have the clarifier removing the solids and sending them back through the system. And so we need to know something about how long the solids themselves are staying in the system, because that tells us about how much solids we are going to have in the system. So let's derive. If we think about theta C, so cell retention time, it's going to be like, well, first of all, if we think about when we do this for water, it's V over Q, right? So V over Q for regular theta, that's going to be the volume of water divided by the flow rate, which is volume per time. So that's going to give us time. So for a solids retention time, rather than just volume of water, we're going to need the mass of microbes. So it's going to be the mass of microbes divided by some term that tells us about the flow of microbes through the system. Okay, so theta C then should be something like mass of X divided by flow of X, or something kind of like that, right? Just kind of big picture, we're thinking about it, how we defined it. That's going to tell us a time value for microbes staying there. So coming back here, theta C, if we say V times Q, instead of just having V times X, instead of just having V over Q, we have V times X. So that gives us the mass, right? That's mass of microbes. Because X is a concentration, V is a volume. Volume times the concentration gives us a mass, if it's a mass concentration. And then on the bottom, we're going to have Q times X. Just like we went from V over Q to Vx, it would make sense that we need Qx, right? In order to kind of satisfy that. But it's not quite that simple because we have QE and QW, right? We have these guys and these guys. So when we write it then, we need a QE times XE plus QW times XW. So that gives us the total outflows of bacteria in the system. But overall, we're still tracking very closely to the way we think about hydraulic retention time. We could call this V over QE plus QW, right? We said earlier that Q equals QE plus QW, right? So that part still holds true for regular theta. So then it would still hold true if we just multiply the top and the bottom by X, right? That can still make sense. If we do X up here and X down here, just multiply it across. That's what's giving us this guy here. Okay, so it kind of makes some sense how we can describe it in that manner. Now, if we remember, we said XE should be 0. And if that's 0, that gives us a bit of a simpler term, and it shows us we've kind of changed the system. We've caused that divergence from the flow just going straight out. So theta c then would change if we were to recycle some stuff. So here we have theta c equals Vx over Qw times Xw. That's really just accounting for the fact that the only place the solids can go in the system is out this waste-activated sludge line. So that's the only place we can discharge. The X can escape anywhere, right? If the clarifier is perfect, it has no other place to go. So that means we could just stop running this waste-activated sludge line, and we'll just have a continuous accumulation of more and more mass of bacteria. Would never do that because that wouldn't make any sense. This also means QW controls a whole lot about the system. It will control X. It'll give us a way to control the food to mass ratio because it's controlling X. This QW here is extremely important for wastewater treatment, it turns out. It's just how much sludge do you allow to go away? And that's because we're managing, just with that one valve, essentially, so much about our system. So that last line, if you talk to a wastewater operator, I'm sure that they can talk quite a bit to you about their operation of the last line and its importance, or what flow they typically do, or any wastewater operator will understand that parameter is quite important. And this is essentially why it's telling us, it's controlling for us how much X we have in the system. Okay, which, like we said earlier, controls the food to mass ratio and all of these other things. And again, if the clarifier is not perfect, if we have a sludge flotation event, that entire control system goes out the window and is a very bad and smelly day. Okay, so for the rest of the class, I want to kind of take our time going through this problem here. And before we do that, I forgot. I meant to tell you, I have graded the exams. I have not compiled them and entered them yet. So I need to do that. But I'll have those back to you on Thursday, and we'll go over those on Thursday. We'll probably start a little bit of the BUD section there. So probably a partial lecture next week, but also pass back the exams. Okay. So for the rest of today, then, I want to kind of step through this practice problem. The first part of it is kind of going through the same stuff we did last week, in terms of, hey, here's a pond-like system. So I'll encourage you to tackle that on your own if you'd like to. I'll just write up kind of a quick reminder, and you can see the example we did last time. We have parameters here that are different than what we used last time and such. So you'll have these notes posted. I may also post just this example problem, if that's helpful. So we'll take a look through it, and then we'll get to the parts of it that apply what we learned today, and we'll take some time on those. Okay, so this problem says, consider a wastewater treatment plant that is being renovated to include a return activated sludge line, RAS. Assume the influent MLVSS, that's I think I said last time, mixed liquor volatile suspended solids. That's the another term for our X. So X concentration in the influent is 0 without the recycle line. That's saying X0 equals 0 with no recycle, or in the case where there's no recycle. Basically, that's kind of like the pond, right? We had no influent X concentration unless we recycle. And we have the following parameters known about the reactor, which acts as a CSTR. So it gives us all sorts of stuff here. And so the first part of the problem says, A, draw a schematic of the activated sludge system before and after the addition of a recycle line. So take a moment to do that, just to be sure that you are understanding what I mean by the activated sludge system and the inclusion of this recycle line. Okay, so before it should look something like a pretty standard CSTR here. Q coming in, X naught, S naught, in some volume. It's well mixed. Q, S, and X leaving. After you add a recycle line, then we're dealing essentially with what we talked about today, where we have, in order to have a recycle line, we have to have a clarifier, separate. And so operating a recycle line is going to look like this, right? So basically the drawing we've been looking at and talking about all day today. It's not going to make any sense to recycle everything. So we're going to have a QW here. So we're going to have S and XW. We'll have Q recycle. Yes, we could talk about S there. Also have our XW here. Could call it XR, but it's the same thing as the XW here. And of course we have QE, S, and XE there. And our Q, X naught, and S naught coming in. So when we say we're adding a recycle line, it is going to entail some clarifier or other separation thing. Side note here, there are such things as membrane bioreactors. And in a membrane bioreactor, we use a membrane instead of a clarifier. It could be just a membrane submersed into the actual system, or it could be like a side stream operation where we pull some water out, separate. And then essentially, instead of taking QW from the clarifier, we would probably just take it from right at the membrane or just from within the tank somewhere. Just remove some at regular, with regular amounts to control the solids. Membrane bioreactors are pretty interesting because you can separate with much more rigor, let's say, at high concentrations of bacteria than a sedimentation chamber can. So you can operate with higher concentrations of bacteria, and that means that you can get better treatment outcomes typically, but it's a little bit higher infrastructure cost. So there's some trade-offs there. Membrane bioreactors are most often used when space constraints are significant, because then you make very good use of that higher concentration, requiring less space to do the treatment. They're becoming a little bit more and more popular, but again, it's there are some cost trade-offs there that are not always financially worthwhile. Okay, so part B says, for this problem, what is the final substrate concentration in the no recycle system? So that's before we added any recycled activated sludge. So this is just like our pond problem. This is going to require that mass balance on X to solve for that S equals stuff. Since it's a CSTR and there's no recycle, that equation I told you I was giving you, it's on the formula sheet. I think I posted that. I'll try to double check today. Should have that formula sheet up. You can use that and solve this problem there. So I'm going to let that be something, if you'd like to do that on your own, you are welcome to. So C and D then are basically the same as that problem we went through last time as well, with the efficiency being just a very generic efficiency term, right? What we started with minus what we removed, divided by what we started with, times 100%. And then part D says, what is the MLVSS? Again, that's asking for X with a no recycled line. Again, that's the pond system where we did a mass balance on S, given that we now know something about S to solve for X. Okay, so same thing there. If you'd like to work that on your own, I would encourage you to do so. So then part E says, if the sludge produced has a concentration of 12,500 milligrams VSS per liter, which is now recycled via the new recycle line, at a flow of 150 cubic meters per day, what is the resulting influent MLVSS concentration entering the aeration tank? And I'm saying refer to your drawing here and do not overthink this problem. Okay, so I've given this on an exam before, and routinely people overthink it. Okay, so I'm going to write up some of the formulas we used today, but when I'm saying don't overthink it, don't assume you have to use all the formulas, right? So I'm going to jog your memory and get these up here based on what we just covered, but draw it up for yourself or take a look back at your drawing and process what that is asking for you to do, okay? Make sure I get this right. going to give you a couple minutes for that. How are you feeling? Got an answer? Yeah. just feel like you understand what the question's asking for. Mostly. All right, so I'm going to go ahead and walk you through this here. So essentially, we're looking at this little juncture that I just circled, right? We are asked to find, given all this stuff, given an X in the recycle, so it says sludge is produced at a concentration of 12,500 milligrams VSS per liter. So that's going to be essentially our recycle concentration. And we're given a flow rate for the recycle at 150 cubic meters per day. Given that, what is the resulting influent ml/VSS concentration entering the aeration tank? And so I say, hint, refer to your drawing and do not overthink the problem. So really what we're looking at is we have QR and XR, we have a Q and an X naught, and we just need to know what the X here is, right? So we know Q from the problem text itself. We find that. At least I assume we do. Yeah, 0.01 cubic meters per second. We have X naught equals 0. And so essentially we have a situation where what's coming in is equal to what's going out, right? So QX naught equals Q, let's see, what's coming in is Qx naught plus QR XR, which is equal to Q, this some sort of new Q, right? That the Q plus QR times this X that we're not sure about, that we need to solve for, okay? So it really is just a mass balance without any fancy stuff. It's just two inputs, one output, and no reaction, none of that, right? So it's, what we need to solve for then is X naught prime thing, whatever we want to call it, is going to be equal to, well, this part goes to 0, so it's going to be simply QR XR divided by the new Q, Q plus QR. Okay, could even divide the top and the bottom by QR, and that gives us XR divided by Q over QR plus 1. So X naught prime here then. Now we will need to convert the Q's to be the same, and so if we take 0.01 cubic meters per second, and notice that 150 cubic meters per day are quite different. Let's go ahead and multiply this guy by 86,400 seconds per day, I think. Got a calculator. Well, actually, I don't need a calculator, do I? So that should be just removing two decimal places, right? So 864. I'm doing that wrong. No. Is that right? Yeah. Okay. Sorry. Had a moment. Okay. So if we take that, then we can put in these numbers and say that's going to be 150 cubic meters per day times the XR, which is 12,500 milligrams per liter. Divide all that by essentially 864 plus 150 should be just over 1,000. 1,014. It's okay that we're leaving this in cubic meters because those are going to cancel, and we'll be left with milligrams per liter. So if we take that then, say 150 times 12,500, divide that by 1,014, should get 1,850 and change milligrams VSS per liter. Okay. How many of you overthought that? Yeah? Some of you? A little bit? Does it make sense now that we've talked about it? Sort of, maybe. The process itself of taking like what's going in equals what's going out makes sense, right? We've been doing that for a while. So the wording then is probably the challenge. And so when I'm telling you to stop and think about what it specifically means, like that's probably where confusion might come in, and simply labeling things carefully should help with that. Okay. All right. So one thing we can take a look at is, first of all, we have a large flow rate coming into the system entirely, a concentrated amount of bacteria coming through. So this X naught should be greater than 0, pretty obviously, right? We're recycling the bacteria. but x naught was 0, so it should be diluting it compared to what's in the recycled line. So this should be between 0 and that 12,500. Sure enough, it is between those two numbers. So it's a small check we can make to say, okay, that seems like it could be reasonable. Even as we were looking at this, it should actually be a function of the ratio of how much we're recycling. And we can get that if we divide the top and the bottom over here by QR. We'll be left with a ratio of Q compared to QR. So it can actually show up mathematically there. Okay, so part F then says, in the new system with the recycle line, the resulting food to mass ratio is 0.58 milligrams BOD per milligrams VSS per day. What will the new MLVSS concentration be in milligrams VSS per liter? So I'm going to write these equations up, give you a moment to work on that. Make sure. Oops. Take a minute to work on that. Okay, so again here we see that it's definitely possible to overthink what's going on here. We're given a value, the food to mass ratio. We're asked for what's the new X concentration in this particular system. And well, we know something about each of these components. We're given the food to mass in a day term, so we're going to use the Q that we solved a minute ago that was 0.01 times the 86,400 cubic meters seconds per day. So I'm going to say that's 864 cubic meters per day times the S naught, which was given 220 milligrams per liter of BOD. Divide all that by the food to mass ratio that was given, and our volume should also be in cubic meters to satisfy the flow rate, which it is. Okay, so with that, we should have units canceling all around. The cubic meters, the days, the milligrams BOD. And so we're going to be left with milligrams VSS that comes to the top and liters as its denominator. So that should give us a value of milligrams per liter VSS. Does anybody have that number for me?
595.86.
Okay. Okay, so again, that's relatively simple or straightforward, given how much of the growth rates and all of that we talked about last time. To truly understand the system and to figure out what's going on, well, if we can simplify it, have a steady state system, we typically don't need to go into that much depth. Last problem here says, well, not quite the last. This is what is the flow rate of the waste activated sludge line. Gives a value for you to assume if you didn't find a reasonable value previously. This is going to refer to the solids retention time, which we said was Qx divided by Qw xw, right? That was our equation for that. And then the last little part is going to be asking about, so I meant to say Vx, I'm sorry. So this will be solve for Qw. And we should have all that known, right? So I'm not going to do that this moment, but that should be pretty straightforward. Last part was, okay, well, what about the hydraulic retention time? It's before and after. It's going to remain the same. That's the trick of it, right? The addition of the recycle line does not change the hydraulic retention time. That's going to be theta equals V over Q, using the volume of the reactor and the flow rate going through the entire system, right? So this would be 550 cubic meters divided by 0.01 cubic meters per second. All right. Any questions or issues? All right. So I'll get you a homework posted. Probably going to focus on the exams for Thursday. So I'll give it to you before the holidays for sure. And we'll be doing kind of what happens downstream of a wastewater treatment plant, starting up next time we're dealing with lecture material. All right, so we'll see you on Thursday.